All right, Feng, in a minute, let's get started. Let's play the dean's message, and then we do the presentation.
Sure.
Let me see how many people are here.
11 participants.
Wow, that's good. Anybody?
Hi, Navid, I'm here.
Hi, Dr. Raj. Good morning.
Good morning, good morning.
All right, let's begin.
I see that our Vodafone liaison is here. That's great. So, and regardless, we are recording this for other people that are interested. All right, so do you want to play the dean's message first?
Yes. Well, hello everyone. Thank you for attending the Smart Eye Drops Expo today. Before we begin, let's play the intro from our Dean and Director of Capstone Senior Design.
Hi everyone, I'm Emily Allen, Dean of the College of Engineering, Computer Science and Technology at Cal State LA, and I'm here to welcome you to our virtual Capstone Expo 2020. That's the Expo that's virtual, not the Capstone projects. In fact, our student teams have been working on their projects since our kickoff in August 2019. That seems like a long time ago now, as the COVID-19 pandemic has forced us into physically distant but socially cohesive modes of operation. We have over 100 project presentations to share live with you over Zoom connections. We are very proud of our excellent senior design program as it rivals programs nationwide in meeting curricular requirements for design. Engineering design is an iterative, creative, problem-solving process in which science, mathematics, and engineering and computing principles are applied to convert resources into solutions. It has a direct and vital impact on the quality of life for all people. With these stakes in mind, our students have been working hard all year long, and especially these past few months, to finish their projects. And these presentations represent the culminating efforts for their degree programs. We deeply appreciate our project sponsors and industry liaisons, our faculty advisors, and the teams that manage and provide instruction for these capstone courses, including Mike Thorburn and Chris Bachman, John Shamma, Howard Lum, Jason Song, and Rupa Purasengi, Paul Liu, Elaine Kang, Jungshu Lim, and Raj Pamula, as well as our staff members, Hasmeek Simon and Evelyn Lee. Now, on with the shows online. Hi, everyone.
Hi, everybody. I'm Mike Thorburn, and on behalf of the Cal State University, Los Angeles, and the College of Engineering, Computer Science and Technology, I want to welcome you to the 2020 Engineering, Computer Science and Technology Capstone Senior Design Expo. This year, it's a truly unique experience for us and for you, as the Expo will be done live via Zoom. Additionally, sessions will be recorded for those not able to participate in the live event. The students have all worked especially hard to make this event happen and to ensure the audience is able to participate from a safe social distance. Between mechanical engineering, electrical engineering, computer science, civil engineering, and technology, we have about 100 presentations scheduled over a period of about 2 weeks. I encourage you to participate constructively in as many as you can. Your feedback is critically important to the students. As you're watching this video, you must already know about our webpage. If you take time to go through it, you'll find detail about all of the presentations and projects. Cal State LA is protecting the event from mischief by using passwords, but if you request access, we'll happily send it to you. The students have been working on their project since August of 2019. Obviously, the COVID-19 epidemic was a huge disruption over the last month and a half, and it's been hard for everybody. I'm proud to say our Cal State LA Engineering, Computer Science and Technology students, just as they have always done, have shown great persistence to overcome the obstacles confronting them and have made a tremendous effort to wrap up their projects and present them to you now. On behalf of the university and on behalf of these terrific students, I welcome you to Expo 2020.
All right, I would like to welcome everyone. I would like to thank our sponsor Vodafone and our liaison Haley Kirk. She told me that she may join us and she finally joined, so I appreciate that. And I would like to thank everybody who is part of this Zoom meeting right now. Thanks a lot for your time. And of course, I would like to thank the group that was able to finish this project despite these hard times. So Feng, let's get started.
Before we begin, I saw some other people joining our meeting, and if I go into presentation mode, I'm not able to admit anyone else. Hello, are you able to hear me?
I can hear you. So that's fine. I don't expect more people. We have at least 2 faculty members and our liaison is here. So okay. I think that's fine. You could ignore that, but it would be nice if 10 minutes into the presentation, you just check quickly and see if when you're not presenting, you just check quickly and see if there is a significant guest that needs to be allowed in. With that, let's get started.
Yeah, I tried that, but it's on with the show. Okay, I got it. So thank you to Dr. Emily Allen and Michael Thorburn for making this expo possible in these extraordinary times, and a very special thank you to our sponsor, Vodafone Group, for supporting our project. My name is Feng. I'm the team lead for Smart Eye Drops, and I'm here today to talk about our project with my team members, Marco, Aaron, Anna, Jonathan, and Ivan. We set out by defining what we wanted to accomplish, which was to build an eye drop adherence monitor that can help reduce blindness caused by diseases such as glaucoma. And why are we doing this? Well, glaucoma is the second leading cause of irreversible blindness worldwide, and more than 3 million Americans are living with glaucoma, 90% of whom are over the age of 40. In a study done by glaucoma specialists, that number is projected to reach more than 7 million people in 2050, growing at a rate of 28% per decade. Studies have also reported that non-adherence for glaucoma ranges from 24 to 59%. This number is given in a range because the current ability of physicians to accurately measure adherence rates are poor. It was found that glaucoma patients tend to stop using their medication after they feel a slight improvement. There are serious consequences that come with this, but studying these side effects can be challenging if people are not taking their medication as prescribed. By creating a smart eye drop bottle, we can ensure that patients abide by the instructions provided by their physicians. Using the data we collect, physicians will be able to make personalized prescription regimens for their patients, enable physicians to analyze whether the treatment plan is working or not, and allow physicians more control outside of their office. This can allow us to cut back significantly on over $2 billion every year in direct costs and productivity losses. According to the Center for Disease Control, every 10% improvement in adherence saves about 29% in healthcare costs. We laid out the following requirements for smart eye drops. First, we want to develop a completely new eye drop adherence monitoring system. There have been other projects in the past that have tried to accomplish a similar goal, but might have had some issues when trying to implement all of the features or requirements. Our goal is to reduce some of these obstacles while trying to build a more robust eye drop adherence application. Our next requirement is to accurately record when patients take their prescription while minimizing noisy data. This is a key requirement that will ensure that the physician is not receiving the wrong information. Lastly, we want to provide physicians with valuable and meaningful information to help them make better decisions on treating their patients. Here's a brief overview of how Smart Eye Drops works. From left going right, when the user of Smart Eye Drops applies their medication, raw data is sent and pass through 6 modules, and meaningful information is displayed. To elaborate on how each module communicates with one another, when the user applies the eye drops, the raw data collected is passed through our data transmission module and sent in real time to our mobile app. From there, the raw data is passed on to our server, where it will forward the data to our machine learning module to be classified as eye drop applied or false entry. Then the classified data is sent to our database to be stored. And finally, when our mobile app is open, classified data from our database will go through our visualization module, and meaningful data will be shown on our adherence graph. And next, I'll call upon Anna to talk about the technologies that we use.
I'm going to do an overview on the technologies we use. Ambient Lab is the company that provided us with our main sensor. We use Ambient Lab's API to start programming. Ambient Lab already has a functional software compatible with its sensors. We use their software to get an idea as to how we could get our project running, since we would be using external force sensors. We use their mobile app to help us collect data for the machine learning portion. We use many of AWS's services for smart eye drops. These are just a few that we used: EC2, SageMaker, and DynamoDB. Smart eye drops is an Android application that will be useful for medical care providers. We are using Android Studio, and the app is written in Java. This is what our hardware consists of. We use Ambient Lab's MetaMotion C, which is a quarter-size sensor, and Ambient Lab's MetaMotion R, which is slightly bigger and is rectangular. Although they both have many features, we focused on retrieving data from the gyroscope and accelerometer. These sensors provide us with real-time sensor data. We needed a force sensor that would help detect the squeezing motion of the eye bottle. The force sensor we decided to use is the one in the bottom of the screen, the FSR Model 406 from Interlink Electronics. This is our prototype. We use the MMR for our prototype because although it is slightly bigger and rectangular, it has a rechargeable battery, while the MMC must have its battery changed. Having a rechargeable battery makes it convenient for the patients who can treat this as an electronic device. The MMR and the FSR 406 are attached to an eye bottle. In order to do this, we first had to attach the force sensor to the MMR through the pins that it has. We tested if the force sensor would work with the MMR and the MMC with a breadboard and resistors before we attached it to the eye bottle. The dimensions of the prototype are 8 centimeters in height and 3 centimeters in width. We were originally planning on 3D printing a case to encapsulate the bottle and the sensor, but because of the pandemic, we were not able to. The width is a little bulky because the MMR has a case to protect it. Regardless, it is still a very convenient size. Now I will pass it on to Aaron and Marco, who will go over mobile development.
You're muted, Aaron.
Sorry, thank you. A key component of this project is being able to make predictions of a user. In order to make predictions, we need data, and lots of it. Gathering data is a key essential part of the Smart Eye Drops project. Our approach was to gather live data as a user is using the Smart Eye Drops bottle. Like I mentioned, we need to gather data in order to make predictions, which means that our Smart Eye Drops bottle prototype has a sensor very similar to the one you see here. This sensor contains smaller components that allows us to gather valuable data. One of those components is an accelerometer sensor. This allows us to calculate acceleration, which in return helps us identify whether a bottle is being picked up. The other components is the metalware pins, which are located at the bottom of the sensor. These pins allows us to install external sensors. One of those external sensors we were able to install was a force sensor. This allows us to calculate force, which in return helps us identify whether the bottle is being pressured. The components allows us to calculate data, but we still need a way to communicate with these components. Luckily, the metalware sensor includes the metalware API library. These are tools that allows us to communicate with these components. Now, gathering data can be messy. There's lots of things handling behind the scenes, which I won't bore you with, but it boils down to this: collecting and packaging data in such a way that allows us to process it effortlessly in the cloud. Eventually, once all that data is being packaged in the cloud, we need to find a way to display our end results. We created an interactive user experience which allows us to visualize the end results. I would now let Marco explain a little bit more about that user experience.
So another feature of the Smart Eye Drops application is the physician view, or rather the physician's profile. This portion of the app gives the physician direct access to their list of patients. From here, the physician is able to send a message to their patients if they like, or click the view button to check up on the patient's progress and view their adherence graph for a particular month. On the graph, you'll see that there are two types of data points. One for the scheduled eye drop use, which are displayed using the gray points on the graph, and the blue data points, which highlight when the patient actually applied the eye drop. Using this information, the physician will be able to visualize the data clearly and adjust the patient's eye drop regimen if he or she feels it is necessary. So I'm briefly going to be going over the communication flow of the AWS services, and then I'll be handing it off to my colleague, Ivan Yu. Next slide. So the Smart Eye Drops app will be sending requests and receiving responses from API Gateway, which acts as the middleman between the user interface and the backend. API Gateway communicates with AWS Lambda and triggers the function responsible for reading and writing to the database. On the bottom portion of the flow diagram, you will see that the mobile application is also communicating with EC2, which provides the server responsible for applying the machine learning algorithms to our data via SageMaker. Once the data is classified, it's stored away onto the database. And now Ivan will be giving a deeper explanation on how we use these AWS services.
So I'm going to be going over the AWS services that we use, starting with API Gateway. So what is API Gateway? API Gateway is like the front door of our application. It lets us walk into a home and talk to each member of that home. API Gateway allows us to create our own API. In our case, we created a HTTP-based API, which lets us make get, post, put, and delete requests to our Lambda application. That brings me into Lambda. So what is AWS Lambda? AWS Lambda is a serverless computing platform. That means it allows us to create virtually any type of application and running it without any servers. We're currently using AWS Lambda to communicate with our database. This includes applications that allow us to write, read, and delete from our DynamoDB. We are also currently using EC2. EC2 is a web service that provides secure, resizable compute capacity. It is essentially a virtual machine, and we are currently using EC2 to process raw data and invoking SageMaker to make predictions and adding that to our DynamoDB. You probably heard me say DynamoDB multiple times already. So what exactly is DynamoDB? DynamoDB is Amazon's database service. It supports key value data structures, which is exactly how we're using it. For example, every physician has an ID, and we can look that up in order to pull up a list of his patients. Another example would be that every patient has an ID, and we can look that up to pull up the full adherence record of the patient. Finally, we use AWS SageMaker for all our machine learning needs. AWS SageMaker is a service that specifically targets machine learning and data science, and we are currently using SageMaker to host all our models and make prediction on adherence. I'll now be passing it on to Jonathan, who will go further into the machine learning aspect of our project.
Before we actually started working with machine learning, we did simple thresholding on the data set that was sent over to EC2. To determine if the eye drop was used, the accelerometer sensor had to detect a change in one of its axes from positive to negative or negative to positive, which will determine that the eye drop bottle had been flipped upside down. The force sensor also had to be squeezed past a certain amount of force for a specific amount of time. If these two happen, then that will determine that the eye drop bottle has been used. Even though it was easy to implement these, it was not very accurate, and sometimes it would not be able to determine the eye drop bottle was used due to many different methods of applying the eye drop. So the machine learning algorithm that we used was long short-term memory. It is a type of recurrent neural network. The algorithm learns from long-term dependencies, which from long-term dependencies, we can get a desired output that depends on inputs presented in the far past. It avoids one of the many problems for recurrent networks. That is that it avoids the dependency problems by holding onto information for longer periods of time. So the way we collected the data was from intervals of 20 seconds, gathering a total of 492 data sets for each eyedrop application. All 491 data sets was turned into one set of features. The features we got were things such as the average, the minimum kurtosis from each axis, the X, Y, Z, and the force sensor. And we got a total of 36 features. When we gathered the features, we were able to label each data set according to the type of applications, such as 1 drop, 2 drops, no drops, walking around, standing still, and accidentally dropping the bottle. Our data is then trained on the machine learning model on SageMaker, where it will be able to make predictions on new incoming data. If it was predicted to either be 1 or 2 drops, then DynamoDB, which is our database server, will be updated. If not, then the data will be discarded. The challenges that we faced when working on this project was learning how to interconnect all the services using AWS, working with hardware even though we are software developers, and working with libraries that did not really have that good documentation. So to summarize what we have accomplished, we were able to collect live data from the sensors. We built a fully functional prototype. We were able to stream and collect data from AWS to display onto our mobile application. And we were also able to implement a machine learning algorithm. And that is the end of our presentation. Next, we will show you a quick video demo on the application of our app.
So I'll be doing the smart eyedrop application demo. Here on my desktop, I have our Android application emulated so that we'll be able to see the update that happens to our database system more clearly. I also have the same application on my phone, and I'll be using that to gather data from our sensors, which are here. To start off, I'll start by applying an eyedrop, and I'll demonstrate the process that happens throughout this entire demo. So once I have applied an eyedrop, our application on our phone will send that data over to the server, which is on EC2. Once the server it's there, the server will process our data into features, and these features will then be sent over to SageMaker, where our machine learning algorithm is. There, it will determine whether our application was either applied correctly or incorrectly. If it was applied correctly, it will update DynamoDB, which is where our database system is. And I'll show you that right now. I'm refreshing it so that we could see the update that has happened to DynamoDB. And at the time of this recording, it's April 27, 8:52 p.m. And that's the time that has been applied. Once it has been applied, once the DynamoDB has been updated, I'll have to refresh the chart, which is on my emulator. And we can see that there has been an update on this charts. The way it gathers this update is by using API Gateway and Lambda to gather the information from DynamoDB. And that is the end of our demo. So I'll be doing.
Excellent. So Haley Kirk, our liaison, she had to leave. She had a conference call just now. But she sent me 2 questions to ask you guys. The first one is the schedule that you show on your mobile phone on the emulator. Do we have a version, a web-based version?
No.
And how hard would it be to turn it into a web-based app as well? So we have 2 versions. We have a mobile app and we have a web app.
It wouldn't be too difficult. A lot of the services are actually interchangeable through whether it's making an app or making a web app. A lot of the service can be reused.
Right.
Actually,
I think the reason she asked this was I sent her the demo and everything is great. So I have to tell you that I'm proud of you, and they were impressed by how much we accomplished in the past effectively 6 months. You know, I wouldn't call this a year-long project because, you know, because of the pandemic. So everybody was impressed, but not exactly with the interface of the app. So the interface looks a little primitive. So she was suggesting maybe we turn it into a web app where we have more real estate to show the schedule, or we make it on the mobile app nicer. Okay. So that's something to think about. You know, of course, I will write a longer answer to her. The second question is the lifetime. She was asking about the battery lifetime of the version that's chargeable, which is the MMC-based version. Do you guys have any idea about the battery lifetime? I'm sure you had to charge the device, but did you come across how many hours could this smart eye drop go without having to be charged?
Well, the MMC does have a bigger capacity battery at 200 milliamps, whereas the MMR has the smaller, it's 70 to 100 milliamp, but that one is the rechargeable one. As for testing, I'm not sure like how long each charge lasted us.
The last for the MMC, I believe it lasted for maybe almost a whole month.
Wow, that's excellent.
And the MMR, it probably, with a full charge, it could probably last 2 to 3 weeks.
That's excellent. So that means the user, so it's not like a smartphone that you need to charge once a day or once every 2 days. So this is something that's convenient. You charge it once a month. So that's not a huge burden on the user. That's excellent. And then this is from me. So I asked her questions. This is from me. So what we call the physician view could actually be the patient's view too. So I think we discussed this, right?
Yes.
So
yes.
As a user, I would like to see how I performed in the past year or in the past month. And as a physician, I would like to see how my patient is performing. So I would say both are equally important. So we need to change our app in a way that it has the physician view and it has the patient view. And the difference is minimal. It's just probably the account is different. Or maybe if you want to add later something for the physician, we could do that. But at this stage of the project, they would look very similar, but we need to have two different views. Okay. So these were all the questions on my side and on the Liaison side. Is there any questions from the audience who joined us, and we thank them?
Yeah, this is John Hurley. Yeah, very nice project, and very nice, well-planned presentation also. In the past, when we've had projects that involved electronics, there often tended to be a lot of problems. So it's really good, especially when you guys did all the electronics yourself?
Yes.
As opposed to, yeah, in the past we've had projects where there were also teams from electrical engineering or whatever, and sometimes so our past experience with things that had embedded electronics were difficult, but it looks like this worked very smoothly. Yeah, very nice project.
Yeah, ideally, John, we wanted to have one person from electrical engineering, but that's hard because it's just one person. The other people are computer science. Logistically, it's hard, but it definitely helps with the project. So also, it would be nice if in the future we have someone from mechanical engineering for the design of this prototype.
Yeah, if you have someone that can be part of your team rather than a separate team. I think maybe the problem is two separate teams working together, and the the mechanical or the electrical engineers or whatever figure that they have the year to finish their project, but in fact you need their product before you can really make yours work. I think that was typically the problem.
Yes, yes, exactly. Any other questions from the audience?
This is Hishing from Department of Mechanical Engineering. Yeah, overall it's a very good presentation, I should say. I have a question about like how this device is used to detect like the application of eye drops. Did you mainly use IMU sensors? So I think that you had a force sensor also in the system, but from the demonstration, I didn't see that how these data are fused together to draw any conclusions. Can you comment on that?
So the question, Jonathan, is we are using an MMU sensor, which is the motion sensor that we have, the MMC. Also, we have the pressure sensor. So this is the best combination of sensors to avoid cheating, meaning the bottle has to be squeezed and at the same time, the bottle has to be flipped. So we are detecting the application of the bottle, and to the extent possible, we are avoiding cheating or other movements of the eye drop that could, in another product, in a primitive product, could be interpreted as the application of the bottle wrongfully. So Jonathan, the question is, how did we combine the pressure sensor data and the motion sensor data? How are we fusing the data?
Okay, so we just gathered the accelerometer sensor, the x-axis, y-axis, and the z-axis, and we also get the pressure value from the force sensor, and then we just combine those together as an input stream and send it over to where our EC2 server is, and converts each of those four features into more features, such as the minimum, the maximum, the average, and the kurtosis. And this would be really helpful for our machine learning algorithms, so they could detect the variables and the different types of ways people are applying the eye drop based on those variables. And the variables come out very different based on how the eye drop is moved.
Right, so you have 4 time series, and on each time series, you're defining some features,
yes,
such as average, mean, max, kurtosis, so on and so forth.
Yeah.
Are you considering the temporal overlap of these
yes.
features? Do you know what I mean?
Yeah, I believe
I think that deep learning does, but do you have more to add to that?
Not really sure if there's more to add. All I know is that as I said before, there's a time period of 20 seconds where it collects the data, and that data is then sent over, and it converts the data into features. It's just within 20 seconds.
Right, and what's the window size? Do you know?
Window size, as in, can you explain?
So 20 seconds is the interval for which you define these features, or you further break it down?
No, it's just 20 seconds where I define these features.
Got it. Thank you. So Dr. Shin, I hope that we were able to answer your question.
How many, so when you use a machine learning to come up with the features and eventually make a decision to put into 6 different categories, how many data points in total that you used to train the model before the demonstration?
Oh, I believe we got about maybe 7,000, around 7,000 data sets of features.
Mm-hmm. All right. Yeah, thank you. It's good.
Thanks, Dr. Shin.
Thank you.
Any other questions from the audience? All right. So I would like to thank everybody again. You guys did a great job despite the pandemic, and we would like to ask Vodafone to let us continue this project. This project could last forever, as you could tell. So the amount of data that we have is enough to run our machine learning algorithm, but it's nowhere close to a real daily life data set that we see in real life applications of machine learning, such as smart vehicles, for example. So let's continue our work for the next week or so. So we have the report, we have the paper, and some technical work, specifically the ones brought up by our liaison. And this will help us get the project going and keep it alive for the next year. Okay?
Yes.
Anything else to add, Feng?
No, that's it.
All right. Thank you, everybody. I hope you have a nice rest of the day.
Thank you too.
Thank you.
Thanks a lot. Nice job.
Thank you very much. Bye-bye.
Thank you.
Bye.
Okay, and
Since you're
stop recording.
Yeah, I was gonna ask that. Since you're recording.
I'll record.